Hello guys, how are you today? So today I'll be explaining the physics AMS of term 1 week 11. So it's the last AMS of the term. So thank you guys for all your support. I'm glad I was able to help you. One thing I want to say before we start is that I'm not happy about the comments. I've been receiving a lot of comments that are not appropriate for the channel, and I'm not willing to see any of these comments anymore. So please guys, this is one reason why the comments are off in this video. Another reason is that I don't feel comfortable with these comments at all. So either you're gonna comment like this and then I will take a stronger action, such as I might stop if you continue commenting this stuff, or you stop commenting and then I will continue peacefully, because this is not okay for you or for me. Thank you guys for understanding, and let's move on with the video. In order to test the rate of conduction inside different materials, 3 different conducting rods of the same dimensions with corks glued by wax at their ends are heated equally using a Bunsen burner as shown in the figure below. So before we start, I would like to talk about the 3 types of heating we have. We have conduction. Okay, conduction happens in solids, liquids, and gases, but it is the best in solids. A very famous example of conduction is, for example, you have a fire, not the best fire. Okay, let's say that this is our fire. And then we have a spoon, okay? Now, the particles of the fire, which I will draw them in pink, okay? They will be touching the particles of the spoon. So that's how, these are all the particles of the spoon, okay? And by conduction, the particles of the fire, the heat from the fire, they're moving fast because it's hot. It will give kinetic energy to one of the particles of the spoon because it's touching, and then by conduction, it will give to another particle, another particle, another particle, another particle, another particle. Now, why is it best in solids? Because solids are tight and compact. The particles are touching each other. So that's why conduction is when the heat transfer is happening between the particles. They are giving to each other. That's why if they're compact and vibrating and they're close to each other, then this is why it is best at solids. Now, after conduction, we're gonna move on to convection. Convection is a nice process that happens in fluids only. Fluids meaning what? Meaning gases and liquids. So let's take an example, okay? For example, we have a glass. We're gonna make it a blue glass. Inside of the glass we have water. These are the water particles. Water particles are not so close together. They're far from each other, okay? And then we heat. Okay, we're gonna heat this water. Now, by convection, what's gonna happen is this. When you heat the particles at the bottom, these particles, they will expand in volume. So they become what? They become less dense. How is that? We know density, okay, is equal to the mass over volume. So if you're gonna increase the volume, then definitely the density is gonna increase because we're dividing by a bigger number. So they will expand in volume, they will become bigger, and they will float to the top, okay? And of course, the more dense particles which are at the top, they will move to the bottom because they are more dense. So then it creates a flow, a current that we call the convection currents. Don't forget the S, convection current. So this is convection. It happens in fluids, which are gases and liquids. Now finally, the last type of heat is radiation. Radiation can happen in any type, meaning solids, liquids, gases, and even, pay attention, even vacuum. That means, for example, in the sun, from the sun, let's draw, for example, this is the earth and this is the sun. Between the sun and the atmospheric layer, there is a vacuum, and this is how the rays of the sun travel. They travel in the vacuum by radiation. Also, you can say radiation is anything that emits light and heat. Anything that emits light plus heat. So these are the 3 types of heating. Then we move on to this question, okay? They're telling us that they heat these three rods to test the rate of conduction, okay? You should know that copper is the best conductor from out of these three. Then after it, so this is the first, then after it comes the steel rod, which is second, and then finally the fiberglass, which is third. So since they are rods, they are solids, and you're heating one end, what's gonna happen is that it's gonna flow by conduction to the other end until the wax over here is gonna heat, and when it heats it will melt, and then the cork will fall. So definitely it will fall first in the copper rod, then second in the steel rod, and third in the fiberglass rod. They might ask you in the exam, what's the best conductor? It is copper rod. What's the worst conductor? It is fiberglass rod. Now the third cork will fall off from the fiberglass rod, we said. The first cork will fall off from the copper rod, we said, and the second cork will fall off from the steel rod. Now we proceed to question number 2. What are the factors on which the rate of conduction of heat depends? Let's read the options together. The thinner the insulator, the better it insulates? No, think of it like this. If it insulates good, then it's an insulator and you need more of it. So it's not gonna be thinner, it's gonna be thicker. Okay, the first one is wrong. Second one, the smaller the area through which heat can escape, the more heat that escapes. So you're telling me if we have, for example, a glass of water like this and a glass of water like this, definitely the water is gonna escape, first of all, more from the one with the larger surface area. The heat is gonna escape more from the larger surface area. So the smaller the area through which heat can escape, the less, not the more, the less heat that escapes. So the first two are wrong. Then, the thicker the insulator, the slower the rate of heat loss. This is correct, because what's the role of the insulator? The role of the insulator is to slow down the rate of the heat lost. So the thicker, the more we have of the insulator, definitely the slower the rate of the heat lost. Now, the higher the difference in temperature between two sources, the higher the heat loss. Let's take it like this. We have an object over here, which is 100 degrees Celsius. And an object over here which is 0 degrees Celsius. Then we have another object over here which is 49 degrees Celsius and an object over here which is 51 degrees Celsius. Why these numbers? Let's see. When these two objects come into contact, they will lose heat or gain heat. So the 100 degrees Celsius will lose heat and it will give it to the 0 degrees Celsius. So definitely they're going to reach something called thermal equilibrium. When they reach thermal equilibrium, to calculate it, it's going to be 100 degrees Celsius plus 0 degrees Celsius over 2, which is 100 over 2, which is 50 degrees Celsius. But now, that means the 100 degrees Celsius is going to lose 50, and this is going to gain 50, and 50 is a big amount of heat. So it's a bigger heat loss. Whereas here, if you do the same, 49 plus 51 divided by 2, okay, you are then gonna get 50 degrees Celsius. But then the 49 is gonna gain 1 degree Celsius and the 51 is gonna lose 1 degree Celsius. Which one has a greater heat loss or a higher heat loss? It's definitely this, with a bigger difference in temperature. So this one and this one are correct. Then the poorer the conductor, the better it insulates. Yes, so poor conductor equal best, or not best, the better insulator. And also poor insulator equals better conductor. Okay, keep this in mind. So then this is our final option. Now we move on to question number 3. Okay, underline the conditions that should be satisfied in insulation. In insulation, we have 3 conditions that need to be satisfied. First of all, it must be cheap for everyone to be able to afford it, especially in the really hot and the really cold countries. It needs to be effective. It needs to work as well. Otherwise, they will die if they buy it or if they don't buy it. يعني بعيد الشر. And then finally, it needs to be complete. Okay, you need to have a complete insulation. So if you're gonna do insulation for the doors, do also for the windows, okay? Not only for the doors and you leave the windows uninsulated, that's not correct. So looking at our options, we can see only 2, which is cheap and effective. Partial is the opposite of complete, Indoor doesn't make sense. Manual also does not make sense. So it has to be cheap and effective and also complete. Now we move on to question number 4. During convection, like we said, we have the particles. We're gonna heat it. Okay. We have these particles at the bottom. Okay. When you heat these particles at the bottom, what happens is that they will become greater in volume. So volume increases. Since their volume increases, their density is gonna decrease. They're gonna become less dense. Why? Because density is equal to the mass over the volume. If you increase the volume, then the density is gonna decrease. Why? Because we're dividing by a bigger number. So the volume increases, it becomes less dense, and always the less dense will float upward. Okay, so if we're gonna answer, during convection, when a part of a fluid means gas or liquid, is heated, it becomes less dense because the volume increases, so then it tends to float upwards, thus mixing the sample's layers. This is a very common example in diffusion. That's why, for example, if you tried food coloring at home, you have these liquid particles, okay, and then you have these colored particles in between. To make the colored particles move more efficiently, you will heat it, and you will see that if you heat it, it will be faster, because why? They're moving faster than if you don't heat it. Another example for convection they might give you is potassium manganate, I think. Manganate. It's a purple dye, you put it in the water and then you heat the water and then you will see the convection current. So now let us proceed to question number 5. So now we move on to question number 5. Which of the following statements are true about heat transfer by radiation? Okay, please pay attention to this. We say that the heat transferred by radiation is quantized, okay? Quantized means that it has a quantity, it's quantized. Also, radiation emits light, and like a radioactive source will emit light, and irradiation will flow, the heat will flow in electromagnetic waves, okay, in addition to the photons. So it is electromagnetic waves plus photon particles, which are body particles. Another thing is that radiation can travel through vacuum, all right? And remember one thing, the best absorbers are the best radiators. Meaning, the one that absorbs the most heat is the one that will radiate the most heat. So this is all about radiation. Radiation is quantized, it has a quantity, it can be calculated, it emits light, okay? This light is electromagnetic waves, and photons, which are like particles or bodies, they can travel through vacuum, and remember, the best absorbers are the best radiators. So we can say that the energy lost by a body is emitted in portions called quanta. Quanta also means quantized, okay? Then, radiation can be defined as the flow of heat from one place to another by means of electromagnetic waves. This is true. Also, don't forget about the photons. Now here we come to something that is very contradictory. Only hot bodies radiate energy? No. You say all bodies radiate energy. So today, my physics teacher, she gave us an example. This example was like, if you have something that is 10 degrees Celsius in room temperature, it is cold, so you will think it will not radiate energy. But if you put this 10 degrees Celsius in a room that is 3 degrees Celsius, then most definitely it's gonna radiate energy. So no matter the case, not only hot bodies, all bodies radiate energy. Same thing, only cold bodies absorb energy, all bodies absorb energy. Okay, so take it like this. For example, 50 degrees Celsius, that's very hot for us. You will think, oh, it will radiate energy. But if you put it in a room that is 150 degrees Celsius, it's definitely gonna absorb the heat from the 150 degrees Celsius. So all bodies radiate energy and all bodies absorb energy. Only some bodies radiate more, some bodies absorb more. And don't forget, the best absorbers are the best radiators. Then we move on to the final one, which states that a radiation from hot bodies can travel through empty space. Empty space means vacuum, so yes, this is correct. Now we move on to question number 6. Conduction is the flow of what along matter without any flow of what? This is something nice. Let me use the diagram again to explain. We have spoon. Okay, what a horrible spoon I drew. We have my spoon over here that looks like a fish. Okay, and then we're gonna hit the spoon. Oh my goodness, my drawing. Okay. And you remember, we have the particles in the spoon. They are compact, they are close, and they are tight together. As we heat, okay, then the kinetic energy will move from the fire all the way to one particle of the spoon, okay? And it will move to the other one by conduction because they're touching each other. Then the other one also by conduction because it's touching each other. Then etc. etc. It will move until it reaches the end or the extremity of the body. So what's happening is that the heat is flowing, okay? But there is one condition. Are the particles of the spoon, are they shifting? Are they changing? So no. You say conduction is the flow of heat without any flow of matter, because the matter is not shifting, it's not moving up and down, it's staying in its place, it's just giving heat. So we can take another example. For example, you have two bodies of water. One over here is 100 degrees Celsius, the other one over here, let's say it is 50 degrees Celsius. So now if you're gonna mix them together, you're gonna put them in one big bowl, okay? What's gonna happen is that the water temperature is gonna change and soon it will become 75 degrees Celsius. But of course, it's not gonna change by convection, because if you're putting it, the water is not gonna be like, whoa, like this, oh my goodness, no. The particles of the 100 degrees Celsius, because they have more heat, they're gonna give heat to the 50 degrees Celsius without possible motion, without any flow of matter. But then, of course, there are some cases where convection can occur. So that's why we don't always take liquids as an example. We take solids as an example, because solids are the best conductors. Okay? So now we can state confidently that conduction is the flow of heat, because what's flowing? Heat is flowing, heat is being transferred along matter without any flow of matter, because you are not changing the shape or the structure of the matter. You're only changing the kinetic energy and the transfer between them. Now, this is something really nice, okay? Pay attention. They told us which element is the poorest conductor of heat. You might be freaking out. You're like, oh my goodness, I didn't memorize them. Just remember, solid, liquid, gas, they all do conduction, but solid is the best conductor. So looking at this, copper is a solid, iron is a solid, steel is a solid. Is water a solid? Not necessarily. Fiberglass is a solid. So they're all solids except for water. So then we can say that water is the poorest conductor of heat because it is not a solid. We proceed to question number 8. States of matter that convection takes place. Let me repeat the convection process. We have over here a liquid, or let's say a fluid, and it has these particles. Okay, we're gonna heat these particles, and here this is a case of conduction. By conduction, these particles at the bottom are going to get heated, and when they become heated, they will grow in size, they will have a bigger volume, so then they will have a less density, okay? And of course, the ones with the less density are gonna flow upwards. Then it will replace these particles over here. Now these particles become what? They become more dense, and the more dense will flow downwards. So remember, the states of matter that convection, which is this process, takes place in are fluids, and fluids include only gases and liquids. So We move on to question number 9. When a part of a fluid is heated, it becomes less dense. So we're definitely talking about convection. So it tends to float upwards. Other denser parts sink, thus moving downwards. The result is that upward, downward, and lateral currents of fluid movement are created cold. So if you remember in my figure that I drew, we had something like this. And then I told you that once you heat it, okay, the less dense is going to move upward, whereas the more dense is going to move downward. Now this motion over here, or this movement of fluid, is a current, okay? Not only a current, it's many currents. So you say plural, that's why you should say currents, plural. And so then we call this a convection current. So these are convection currents because there are multiple currents. So it can be like this, or like this, or like this, however you want. But you should know that there are multiple currents, like they said, upward, downward, lateral currents, okay? And in general, we call these convection current, and we spell it like this. Okay, so convection, then currents with an S. Do not forget the S because you have more than one current. Now we proceed to question number 10. So here they're telling us the experiment below is conducted to help visualize convection currents in air. So let's take a good look at the experiment. It's not going to fit all of it, as I'll do part by part. Over here we have two tubes or two glass chimneys. The first tube is blocked with a lighted touch paper. Why is it blocked? To prevent gas from to prevent unnecessary, I forgot how to spell it, oh my goodness. Let's just say unimportant. To prevent unimportant gas from escaping. Or like to prevent, let us just say it prevents gases from escaping, okay? Then, if you go down, you will see there is a lighted candle over here. And this is a glass window, so you can see what is happening, and then you have a box surrounding it for better insulation. So we are talking about what? We are talking about convection currents. Now definitely in convection currents, you're going to have dense and less dense, because this is how the convection works. The less dense will float upwards, the dense will float downwards. But dense you can relate to colder objects, and less dense you can relate to hotter objects. So in the exam, if you put dense or cold, it's correct. If you put less dense or hot, it is correct. Now looking at the graph, they're asking us the arrow pointing down. The arrow pointing down is definitely the particles that are going down. So if you remember the representation, we said that after heating it, the less dense will move up and the more dense will move down. So if this one is moving down, that means it is the more dense, okay? So we can say they are the dense particles, whereas the one that is going up, we can call them less dense. Remember, dense we said we can say instead cold, less dense we said instead we can say hot. So to simplify, the arrow pointing down shows cold air going into the box, or dense. I'm going to say dense for this one. Okay? And then the arrow pointing up shows less dense air, or hot air going out of the box. I'm going to put one as dense and the other one as hot to show you that both are correct. So remember, less dense means hot, more dense means cold. Now we proceed to question number 11. This is very nice, okay? This is a very logical experiment. You can see it in daily life. Usually, in the daytimes, the land is hotter than the sea. So what happens is that the sea is gonna cool down the land, okay, by the wind. So if it is hotter, what's gonna happen is that we have wind particles over here, all right? And we have sea particles over here. Since the sand becomes hotter, then it will heat up these the wind particles, and we know due to convection, if you heat something up, it's gonna increase in size, increase in volume, so it's gonna float up. All right? Then after it floats up, it will replace the denser particles that are already found up, and then it will come down. Okay? And then these become colder, and so they come all the way here. They go either to the sea or to the land, and then this is how the breeze happens. We call this a breeze. All right? So again, I will repeat. We have wind particles on the land and wind particles on the sea. Because in the daytime the land is hotter, it's gonna heat the particles of the wind that are present on the land, and they will increase in volume, they will become hotter, and they will flow upwards, and they will replace the air particles that are already found above. Then these air particles, because they become denser than these which are less dense, they will flow to the bottom. They will replace these particles over here, and these particles will move to be instead of the original particles. And then the process occurs over and over again. Now, of course, if it is coming from the sea, then we call it a sea breeze. But if it's coming from the land, then we call it a land breeze. Let me now also explain the land breeze. Now, during the night, what happens is that the sea, okay, its particles become, like the sea becomes hotter than the land. So let's say we have wind particles on the land and wind particles on the sea. Of course, since the sea is hotter, the particles are going to expand in volume, and they're going to float up and replace the already existing air particles at the top. Then the air particles, because they become less dense, they will flow to the bottom and replace these particles over here. And these particles are cold, so they will come all the way and replace the ones of the sea. So then they get hot again, they will go up again, and whatever. So it is basically a cycle, and we call this land breeze. So now, in figure 1, the phenomena of air convection observed is called a sea breeze. So, sea breeze. Then, in figure 2, warm air above the sea rises and is replaced by cold air coming from the land. We call this a land breeze. Now, we move on to question number 12. To stop convection, insulators with many very small what is used? Okay, very simply. Convection is the transfer of heat, and for heat to happen, you need conductors, okay? Now, insulators, they are opposite of conductors. They do not let the heat pass through them. So to stop the convection, to stop the heat from passing, okay, we're gonna use an insulator. And you should know that the best insulators are either vacuum or air. So to stop the convection, insulators that contain vacuum or air are used. So here in our options, we have paper shreds, no, iron fillings, no, solid particles, no, but instead we use the air bubbles. Again, to stop convection, insulators we are gonna use, the best ones are air and vacuum. Now, we go on to Mr. Planck. Now, Max Planck, he is a physicist. He came up with the idea that energy lost by black bodies is what? Is quantized. Remember, we said it before. Quantized. Now, why did they say black bodies over here? You should know that black is what? Is the best absorber. And we said that the best absorber is always the best radiator. And if you remember, in one of the questions we were talking about radiators and radiation, we said that the energy lost by radiation is called quanta, or it is quantized, meaning it has a quantity. That means, of course, there is an equation. The equation that Mr. Max Planck came up with was that the energy of each quanta, which we are going to denote by E, is equal to his constant, which we are going to denote by H. This is Planck's constant, which is a big number, which is almost 6.63 times 10 to the minus of 34. It seems like a big number, but it's very small in fact. So the energy of each quanta, the energy of each particle of black body, we said it's quantized. So the energy of each quanta is equal to his constant, Planck's constant, which is 6.63 times 10 to the minus 34, multiplied by the frequency of radiation. So here they didn't give us any numbers, instead they gave us to write the relation. So we know that the energy of each quanta is equal to his constant h multiplied by f, or you can not divide it, or you can write it as hf. So very simply, you can write it h times f or hf, but it's preferable that you write it as hf. So again, Mr. Planck, he came up with the idea that energy lost by black bodies is quantized. Why? Because black bodies absorb the most and they are the best absorbers, and we know that the best absorbers are the best radiators, and we talked about radiators. We said that the energy lost by radiators is quantized. Why exactly is it quantized? He's basically saying that because radiators give off light, okay, and we know that light is electromagnetic waves plus photons, he is telling us that each photon has a specific color, okay? By the way, for the guy who was asking about my favorite color, okay, you guessed it wrong. Keep on guessing, okay? So what Mr. Planck is saying is that each photon has a specific color. Like, of course, many photons have the same color, but there's like a color spectrum. For example, red, blue, green, violet, I also believe, okay? So each of these photons carry a specific color, all right? Now, each of these photons that has a specific color, they have a different speed. So specific color means specific speed. For example, red has the fastest speed. So if you link a photon to the color red, that means it has the fastest speed. Then, after doing many calculations, he came up with that the energy of this photon that contains this specific color, okay, it's equal to his constant h times the frequency of the color. Of course, the frequency is always given to us, so don't worry about it. Something about black is that it absorbs. I think you guys should know that the black absorbs all colors, okay, whereas white, it reflects all colors. So basically, this is question number 13 done. We proceed to question number 14. How many times did I say the best absorber of a radiant energy is the best radiator? Okay, but don't write this. This is a different question. But what is a good radiator? It's something that absorbs all colors or all the light. And what absorbs all the light? It is the black bodies. Remember, black bodies absorb all the light, so they are the best absorber. So definitely that means they are the best radiators. So our answer over here is black body. We move on to question number 15. The energy carried by a photon of frequency 1.2 times 10 to the power of 15 hertz. The unit of frequency is hertz, and the unit for Planck's constant h is joules per second. And they need us to find the energy carried. So very simply, we're going to write the equation, which is that energy is equal to Planck's constant times the frequency. So it is his constant, which is 6.6 times 10 to the power of minus 34 times 1.2 times 10 to the power of 15. And you are going to get 7.92 times 10 to the power of negative 19. So let's go down. We don't have 7.92, but we have 7.9. Okay, and it was 10 to the power of negative 19. Okay, so now we proceed to question number 16. Now, this is a very nice thing. We have a thermocouple. Let me explain each part of the thermocouple to you. A thermocouple is something you can find in the AC. All in all, the thermocouple detects what? It detects temperature change. Now, this is the thermocouple all in all as one device. Let's break it into different devices. We have meter X that we call a galvanometer. Or, sorry, not a galvanometer, it's a galvanometer. Meter X is a galvanometer. It is used only to measure if we have a current or not. So we use a galvanometer to see if we have a current or not. The thermocouple as a whole, as total, is temperature change. It detects temperature change. Whereas a galvanometer, which is meter X, is used only to see if we have a current or not. Now what happens is that the thermocouple, all in all, it will see, you're gonna set it, for example, the AC, you're gonna say, I want it 20 degrees Celsius. If your room was 25 degrees Celsius, it's gonna say, okay, we need to have a change of 5 degrees Celsius. So it is gonna keep on lowering the temperature by emitting a current by the galvanometer. So it will first detect a temperature change. You will be like, I want a 20 degrees, my room is 25 degrees. It needs a 5 degrees Celsius temperature change. So then what's going to happen is that the meter X will start working, the galvanometer will start working because it will detect a current, okay? And then for this current to work, okay, because of the temperature change, the AC will start to work because of the galvanometer, and then because of the thermocouple in total. So again, I will repeat, or no, I will not repeat, I will add more information. In a thermocouple, we have two different metal materials, okay? So wire W and wire Y are definitely the same because they look the same, whereas wire Z is a different material. So they might give you in the exam, for example, wire Y is copper and wire Z is tungsten. Since wire W and wire Y are both coming out of the galvanometer, they are both made of the same thing, copper. But wire Z, which is a different wire that is not coming from the galvanometer, okay, it is a different material, which is tungsten, for example. Alright, so what does a thermocouple measure? It measures temperature. Then they asked us which wires are made of the same material. We said if they're both coming out of the galvanometer, then they are both definitely from the same material. So W and Y. So if they're both coming out of the galvanometer, then they are the same material. If they're not coming out of the galvanometer, then if it's like a different wire, not coming from the galvanometer, then it's a different material. So W and Y both come out of the galvanometer, so they are the same material. Meter X, which we said is the galvanometer, it measures if we have a current or not. Now we reach to which statements describe a thermocouple correctly. For the thermocouple to detect a change in temperature, it is supposed to have a low heat capacity to act quickly, not a high heat capacity, a low heat capacity so it can act quickly. Then they also have a really high precision, meaning if you turn on the AC and you say, okay, I want it now 15 degrees and your room was 20 degrees, it's gonna detect that your room is 20 degrees and it will know, okay, I need to change the room, I need to lower it by 5 degrees Celsius. And then when it detects that the room is 15 degrees Celsius, it will stop working and then the room will remain a constant as 15 degrees Celsius. So it is highly precise, meaning it has a high precision. It's very accurate. Thermocouples can only measure high temperatures? No, they can measure really low temperatures, really high temperatures. You can check on your AC what's the lowest temperature and what's the highest temperature. But of course, don't damage your AC. Now finally, thermocouples have a slow response. No, they have a high precision, meaning they have a fast response. So definitely the last one is wrong. For part D, we only have two correct, which are low heat capacity, because they need a low heat capacity to act directly. They will not take time to act, whereas they have a relatively high precision. That means they are very accurate. Now we are talking by the kinetic molecular theory. We're talking about molecules, which are particles. What happens when you heat something by conduction? The heat transfer by conduction occurs when the faster moving molecules, so you are heating the spoon, from the fire, we have fast moving molecules, they have a higher kinetic energy. They are also hotter, so if you have a higher kinetic energy, or if you're moving faster, then you are hotter. So what happens is that due to conduction, they are gonna bump into the other particles, they are gonna collide with the slower moving, okay? colder particles, okay? Then after that, because they are bumping to the slower moving particles, they're gonna give them kinetic energy. So that means thus passing on to them a part of their kinetic energy. Then we move on to question number 18. A solid sphere cannot fit into a cylindrical hole as shown below. Very nice example. To make the solid sphere fit, what we are gonna do is that we're gonna either heat, let me use a different color to represent heat. We are gonna either heat the cylindrical hole, or cool the ball. Why? Because heating expands, and when you heat the cylindrical hole, it's gonna expand and become bigger, and then the ball will be able to enter, whereas cooling shrinks. So if you cool the ball, it will shrink in size, it will become smaller, and then it will not be able to, it will be able to pass into the cylindrical hole. Let's take it in the way of particles. If you heat something that has like tense particles that are close and tight together, when you heat it, they will start to have higher kinetic energy, start bumping into each other, okay? And then slowly but surely it's gonna expand, especially for the metals. It will slowly but surely start to expand. Whereas cooling, okay, if the particles were like a little bit loose, they're moving around, they're bumping into each other, they have a lot of kinetic energy. If you cool it down, then the kinetic energy is gonna decrease. And when the kinetic energy decreases, then the particles will become very compact, very close and tight together, and then it will become smaller. Okay, so what's one action that can be done to try fit the solid sphere? You have heat the solid sphere? No, we said you either cool the solid sphere or you heat the cylindrical hole. Now, why does this explain our answer? Because if you cool the solid sphere, then it will shrink and then it will be able to fit inside of the cylindrical hole. Now we move on to question number 19. Again, we have another example. The picture below shows an experiment used to compare different metals. 4 matches are waxed on one end of 4 different metal rods while a Bunsen burner heats the other end. What's going to happen is that by conduction, because this is particles, all of these are particles, they're so close together, the heat will give kinetic energy to this particle, and then it will give to this particle, and etc, etc. All the particles will have kinetic energy, and then the heat will reach to the wax, and the wax will also melt, and when it melts, then the match is gonna fall down. So what are they asking us? They are telling us, how can you tell which metal is the best thermal conductor? Very simply, the best thermal conductors are the ones that the wax is gonna melt first, and the matchstick is gonna fall. So let's see the options. The one that lights up the match last, are you even gonna light up the match? No. The one that loses its match first, definitely. The one that the matchstick will fall down first means it's the best thermal conductor. The one that changes color first, no, we did not say anything about changing color. The one that loses its match last, this is wrong. The one that loses its match last is the worst thermal conductor. And then the one that lights up the match, we are not lighting up the match. So our answer is the one that loses its match first. And now, this is the question I've been waiting for, to explain to you about the radiators. A heat radiator is placed between a white and a black surface as shown below. We know that the white is the best reflector. It reflects all colors, all light, whereas the black is the best absorber. So what happens is that the heat radiator is gonna release heat. The black is gonna take it in. But if the heat radiator releases heat to the white is not gonna take it, it's gonna reflect it back, so it will go back. This is because the white, it reflects all the colors, and the black absorbs all of the colors. Same thing if you were talking about metallic or something shiny, okay, or a mirror, then it will do the same thing as the white surface. It will reflect all of the light, not necessarily metallic, but anything shiny, anything that reflects. So you look at it, you see, does it reflect? Yes, if it reflects, then it's the best reflector, it's the worst absorber. Okay, if it does not reflect, for example, a black surface, and instead it's absorbing all the light, then yes, for sure, it is a good absorber and a bad reflector. Remember what we said, the best absorbers are the best radiators. So this is all I wanted to explain for now. Which surface is the better absorber of heat? Definitely the black surface, because it absorbs all the colors. The best reflector of heat is the white surface, because it's reflecting all of the heat, reflecting all of the colors. And finally, what's the best emitter or the best radiator of heat? We said the best absorber is the best radiator, so definitely it's gonna be the black surface. So let's submit, and inshallah we don't have any mistakes. And alhamdulillah, we don't have any mistakes. Thank you guys for watching. I hope you enjoyed and have a wonderful day.